Welcome to the next class. I have in front of me Amrita, TN. I have two girls see right in front of me. Can you hear me? Can you just wave if you can hear me? Amrita, TN. So it looks like connected to Amrita, TN. Can you hear me? Can you please wave? Okay, yeah, all right. So did you attend the last class where we talked about gradient? We're going to continue from that point because we started the course with a practical problem of taking high frequency signals from a source to a load, and we know how to solve that problem, how to do impedance matching and things like that. But in order to be able to design a desired transmission line, we realize that we want to know a little bit of electromagnetics. So we want to be actually talking about the electric field and magnetic field instead of the voltage wave and the current wave, because the voltage wave and the current wave get associated with the electric field and magnetic field respectively. So to be able to talk about rules that govern the electric field and magnetic field, we said we'll do a very quick review of some of the basic concepts in vector calculus, which is going to be useful for us. And then we go on to electric field and magnetic field. That's what we started last time. We defined scalar, vector. We defined what is line integral, which is essentially the projection of the vector along the contour that you want to, or the line that you want to, you are talking about. We also talked about surface integral, which is essentially talking about the flux of the vector field crossing the surface that we are talking about. Talked about volume integral in a similar way, and we started talking about gradient of a scalar field. And the example I gave you was temperature, which is a scalar, but it could be function of x, y, z. I gave you an example of the temperature of this studio, where at the place which is close to the AC vent, the temperature could be lower. Closer to amplifiers or instruments which are emitting heat, the temperature could be higher. So there is a non-uniform distribution of temperature in this room. Question is, how do I explain the change in temperature, the gradient of temperature in this room? So let's consider this vector space or a three-dimensional space x, y, z. We are considering a point P1. Now you want to know what is the temperature at the point P2. If T is the temperature here, let's say the temperature here is T plus delta T. The question is, knowing the nature of T, knowing the value of T at every position x, y, z in the space, how do I calculate delta T, which is at a specific direction dl defined by a specific x, y, z direction from the point P1. Question we are asking ourselves is, what is the dt between P1 and P2? What is the change in temperature? where I know that P1 is at a temperature T and P2 is at a temperature T plus dt. This is what I want to know. The way you want to do it is without, because I have maybe only 2 or 3 classes left, so I will not do the detailed derivation, but I'll tell you the gist, or I'll tell you the physics or the understanding part of it, right? The physical meaning part of it. dt can be obtained as you calculate del t, the gradient of del is a vector, del t dot dl. So in a way you are finding the projection of del t in the direction dl along which you want to find what is dt. You want to find the dt along dl. It is not necessary that I go in a certain other direction, I get another point P3, distance could be the same, but in a different direction the temperature could be T plus some delta T prime. It is not necessary that there is a uniformly changing distribution of temperature. So it's possible that in different directions the temperature gradient is different. If I go in this direction it could be lower, if I go in this direction it could be higher, or it could be different from the change in temperature could be different. So what is gradient helping you to find? Gradient is helping you to find the directional derivative. Directional derivative in the sense, in a specific direction you want to know what is the change. That is what gradient will help you to tell. So in this specific direction dl, the change in temperature is gradient times dl, gradient dot dl. So magnitude of this gradient, the magnitude tells me the maximum rate of change t, and the direction of del t is the direction in which the rate of maximum change occurs. Simply because this I can write as, you see del t is a vector which could be in this direction, del t could be in this direction, dl could be in another direction, right? And if theta is the angle between del t and dl, I would have dt as magnitude of del t, magnitude of dl cos theta, which means dt equal to the magnitude of del times of course magnitude of dl, which I can say per unit length or per unit magnitude, if theta is 0, which means del t is that value of dt in the direction of maximum, because for any other value of theta my dt is going to be smaller than this number because I have a cos theta component there, which is why we say the magnitude of the gradient tells me the maximum rate of change of t, and along what direction, when theta equal to 0, that is the direction in which the rate of change of maximum, direction in which the rate of change is maximum. Simply speaking, physically what does it mean? It simply means that I have, let us say, a point P, and around P let me draw a contour of constant T. So this is a point P which is having a temperature T. Let us say if I join all the points which have a temperature T plus delta T, this is the contour. So in this direction, if I look at, the change is less, but if I am looking at it in this direction, change is largest. So gradient of T, the magnitude of the gradient of T is telling me what is the maximum rate of change of T, and the direction tells me the direction at which the maximum change happens, right. So that is about the gradient. How do you calculate the gradient? I know that the del operator is Ax del by del x plus Ay del by del y plus Az del by del z, and T is a scalar function which is a function, could be function of x, y, z. So I operate del on T, which means I take the derivative with respect to x, fix it along with Ax, derivative of T with respect to y, fix it along with Ay. Same way, derivative of T with respect to z, fix it along with Az, I get the vector del T. That is my gradient. So gradient in short tells me the rate of the spatial space rate of change of, it tells me the space rate of change in the maximum, in the direction of the maximum change. Going to be useful later, we will come to that. The next concept that we need to remember, or we will keep calling, is divergence of a vector field. Now I am going to be talking about vector field. Now how do I distinguish a scalar field from a vector field? Scalar field talked about, for example, temperature. At different points in space, the temperature is different, but temperature is a scalar, which means it does not have any direction. I do not have to specify that the temperature is 30 degree in y direction or z direction. Direction does not matter, it is a scalar. Whereas in a vector field, I will be talking about a vector which will have x, y, z dependence. So an example is, say this is my coordinate axis. I could have a vector at this particular point in space. The way a vector field is represented is, you need its magnitude and you need the direction. So at every point in space I should be specifying the direction also. So let us say I want to specify this vector field in these 4 points, right, or 6 points. It's possible that the vector field is this. This is an example of a vector field. What are these arrows indicating? These arrows are indicating that this vector field is in the direction of z. The direction of the field is z, and what are the size of the arrows indicating? It's saying that from the xy plane, so this point is, these 2 points are on the xy plane, which is at z equal to 0. At z equal to 0 there is a small magnitude, but as z is increasing, as you keep on increasing z, the magnitude of the vector is increasing. This is some arbitrary vector that I have considered. I can give you another example for vector field. Let us say I have a point charge, a charge q, right. We know Coulomb's law. What does it say? If I have a charge q there is an electric field in the region of space around the charge. If I have a stationary charge, I have an electric field around it, right? Now what quantifies the electric field? What is the strength of that electric field? The moment I say electric field, I should not only quantify the strength, the magnitude, I should also quantify the direction. I should say how much is the electric field and in which direction is the electric field. So how do we do that? From your high school, you know that electric field is the force experienced by unit positive charge. This is the definition probably you have learnt in high school. Electric field due to this charge Q is the force experienced by a unit positive charge placed at that point. So I bring in a unit positive charge and measure the force experienced by this charge at this point. That force is going to tell me the magnitude and direction of the electric field. Because it's a force, it's a vector, it has to tell me the direction. So how do I calculate this magnitude of the force? Magnitude of the force is given by your Coulomb's law, right? If I have a charge Q1 and another charge Q2, then the force experienced by Q2 due to Q1 is a vector whose magnitude is 1 by 4 pi epsilon 0 Q1 Q2 by mod r square, where r is the vector from Q1 to Q2. This is the magnitude. What's the direction? Along unit vector along r. That is the direction. So this is the force experienced. This is your Coulomb's law. So what is the force experienced by unit charge? So electric field is the force experienced by unit charge, which means instead of Q2 I have a unit charge. Or in other words, I can write this as F over Q, where Q with the limit that Q tends to 0. Force experienced by an infinitesimally small charge. That's another way of doing it. So that force is, if I write from here, it is 1 over 4 pi epsilon 0 Q1 by mod r square unit vector r. So if I think Amrita class is not interested in this lecture, so I am going to change to some other class, because it's not a heartening sight to have people having fun out there and there is no moderation in that class. It's not fun to teach that class. So at least better I can do is, the best I can do is not to have their video in front of me. I'm trying to connect to some other class where the students are listening. Because I don't want to be talking to a captive audience who are sitting there and having fun. What is this? do TC or okay. Yeah, VPCOE. SEC. Which is this one, which is the, yeah, just go ahead with it. Yeah. Yeah, so I've moved over to the DCRU college. DCRU, I can see you in front of me. I'll continue my lecture because the college that I projected earlier, which was Amrita, they did not seem to be very interested in this. Looks like they were forced to sit there, and I don't have to necessarily talk to a bunch of people who are probably not very interested in listening. At least I can talk to people who are interested, seemingly. Alright, so we were talking about the electric field. I was trying to give you an example of a vector field. And to give you an example of vector field, we started talking about, the Coulomb's law and force experienced by a unit charge is electric field and so on. So if I pick a charge Q, I want to know, if I want to know the electric field, what I should do is to be able to find out the electric field at each point XYZ in space. Let's say my origin is, I fix my origin at the point where the charge is located, alright, and I want to know what is the electric field at this point. What should I do? I should keep a unit positive charge there and measure the force there. And how much is the force? It is proportional to, inversely proportional to the square of the magnitude of the distance between the point that I am looking at and the origin in this case. So it's going to be proportional to this distance. And what is the direction? It is along this direction. So let me start putting vectors, just like how I gave you an example earlier. Let me just start marking vectors corresponding to each point in space at which I want to, so I want to, let us say, mark the electric field at these points in space. Let's say I want to mark the electric fields at these points. Now I'm trying to draw these 3 points which are equidistant from Q. What is the magnitude? The magnitude is, let's say, this, which is decided by the distance, this distance, and of course the magnitude of charge. Direction is away from this along the vector joining this point and the charge Q. What is the magnitude at this point? The direction is still the same because I am trying to track the electric field along the same line. The direction is the same. What would have happened to the magnitude? The distance has increased, so the force would reduce. It goes as 1 over r square. So if I were to draw the vector, I would draw the vector like this. What would it be here? That would be still a smaller vector. What would it be here? That will be a larger vector. So if I am trying to mark the electric field at each point, that's going to look like this: a bigger vector, a smaller vector, a further smaller vector, and so on. What about these points? Since these 2 points have a distance equal distance with respect to the origin, the magnitude is the same, but the direction has changed. So I would have something like this. If I were to mark here, this would be a larger vector here, smaller vector here, and a smaller vector. It would be something like this. This is a smaller vector. So this is how my field is a function of xyz looking like, and this is a typical example of a vector field in electromagnetics. At every point in space, the direction is different, direction could be different, magnitude could be different. Alright. Now what does gradient tell you? Gradient told you the change, the rate of change of a scalar field. What is divergence going to tell you? Divergence physically is going to tell you how much this vector, by how much is this vector diverging around the point under consideration. So in this particular case I will redraw, this is my Q, around this Q the vector field is, the electric field is behaving this way, around this Q the force experienced is behaving this way. I can intuitively say that at this point Q there is a lot of divergence, vector is diverging out of this point, alright. So divergence tells you by how much is the vector, or physically it gives you an intuition of by how much is the vector diverging out of this point. Let us go back to the example that I considered first. This is an example that I considered first, where I said there is a vector field which is doing this. It is not an electric field, some other vector field, what it represents. What divergence here? Let us say around this point, I am considering this point. What do you think is the divergence there? Do you see vector directions going out or going in to that point? It is not happening, it is all going parallel, which means I can say that this is an example of a case where at this P the divergence is actually 0. It is not diverging out of that point, right. So that is what the divergence tells, the physical meaning of divergence. Now we will go on to the mathematical definition of the divergence. The definition is, or the way it gets defined is the following, which is again similar to what we similar to what the intuition tells you. If I have a vector space x, y, z, I am trying to find the divergence at this point. Let us say I want to find the divergence at this point. What I do is I consider a unit volume. So unit volume around the point P. So P is the point around which I want to consider the divergence. Let me draw that unit volume a little bigger. It is in principle a differential volume, which means it has to be as small as possible, but for clarity I am going to draw this as a large volume, and my point P, this is not my point, the point P is located inside. I have my vector A, x, y, z in this area. Now what I do is I calculate the net outward flux per unit volume around this point. What is the net outward flux? Which means I need to calculate what is the flux entering through the surface A. Let us say the field is doing this. I want to calculate A dot ds across this area. that net outward flux per unit volume in the limit as the volume shrinks to P. Essentially saying that the volume that I am considering now should be infinitesimally small. I'll shrunk this volume, I'll keep on calculating this flux for all the 6 phases in the limit that delta V tends to 0, which means I am shrinking that volume as close to the point as possible. That is my divergence. So, divergence of A, if I write this mathematically, what does it mean? Net outward flux, which means the closed surface integral. So, it is not just surface integral, it is not that just across the surface I calculate the flux over closed surface, which means I have to, if I am considering a volume a 6-phased cube, I have to calculate the surface integral over all the phases. Remember how to calculate surface integral? A dot ds is A ds cos theta. We discussed that last time, how to calculate that. So you have to do that for all the 6 surfaces. That is the net outward flux. In what limit? In the limit, so this is net outward flux per unit volume. So this has to be divided by delta V, the unit volume. In the limit as delta V tends to 0. In the limit that the volume shrinks to 0. That is the definition of divergence. Physically, what does it mean? It means how much is the net divergence would mean how much is the effect of the vector moving out of that point or moving into that point. For example, if I have a vector field like this, I do this operation, I take a unit volume and find out what is the total flux. You will realize that, so if I have, let me use a red pen here. So this is my volume here. I know that there is some flux entering, but the same flux is leaving out through the top face. And since the vector field is pointed along the z direction, I do not have any flux entering or leaving the xy, the planes on the sides, which means in this case the net flux that is entering is the same as the net flux, the flux that is entering is the same as the flux that is leaving, which means the net outward flux is 0, which is why we said intuitively also the divergence is 0. Now this relation is also helping you to define, tell you that suppose I take a unit volume and I keep doing this, it simply also means that the net flux considering a specific volume, I reverse this operation of differentiation. The reverse operation or inverse operation of differentiation is integration. So this would simply mean that A dot ds, the net flux, outward flux, the inverse of this operation would give me divergence of A, integral divergence of A dv. Now this divergence of A is also represented as del dot A, or the, how do you calculate mathematically, it also would lead to del dot A, which means the del operator dotted with A. Is my answer scalar or a vector? My answer is a scalar. The divergence operation will give you a scalar as an answer. So I can write this inverse equation that I wrote down as A dot ds is, this is volume, so I need to take the volume integral. Instead of divergence A, I am just representing it as del dot A dv. Now this relation comes to be called as Gauss's divergence theorem. What is the physical meaning of this theorem? I take a volume V, I find the divergence at every point, integrate that over this volume, which means at every point I find what is the net outward flux. Net outward flux at every point I calculate how much is the net outward flux, integrate it over. Answer is the same as surface integral. Has to be, because that is how divergence got defined. It's a net outward flux is in the volume is divergence. So the answer has to be surface integral. So that's an intuitive way of understanding Gauss's divergence theorem. Because at every point you are calculating how much is the outward flux. If you calculate for the entire volume, that is nothing but the surface integral, nothing but the net outward flux from the volume. So that's about divergence. Remember, divergence answer is a scalar. There's one notation you can do. If divergence 0, it implies that it could be a vector which is not diverging away. What would it be if, what would I understand if my del dot A is, for example, answer, it's a scalar number, suppose it's a negative number. What would it mean? Physically, what does it mean? There is a divergence, but that divergence is negative, which means it is not net outward, it is net inward. So example would be, I could have a negative charge Q and the field could be something like, electric field due to a negative charge is an example of the case where I have negative divergence. Because there again the vector is inwards, because the force experienced by the unit positive charge is now inwards. So as distance increases, the strength of the force goes on decreasing. So here again it is diverging, but it is not outward, it is inward. Okay, the next concept that you want to be knowing in electromagnetics is curl of a vector. Now, divergence was telling you how much is the vector spreading out, whereas curl is going to tell you how much is the vector rotating. Effect of circulation or rotation. So again, it's easier to understand the interpretation physically with an example vector field. What's happened? Page. All right. So let us say I have a vector, I have a point here. This is again a vector curl of a vector field, which means I have something like an electric field whose magnitude is changing with position, whose direction also is changing with position. Let us say I have a vector field around this point P. If I look at the vector field is at every point I am trying to look at what is the magnitude of this field around this point. I have, let us say, magnitude same, but only the direction changing, and the direction is such that it is rotating. This is a classic case where I have a large curl. Curl tells you how much is the vector rotating. I will give an example for curl, one more example, practical example. I take two plates of a capacitor, okay, they are intended to be straight parallel plates of a capacitor. Let us say this has plus Q charge, side has a minus Q charge. Now I want to know what is the electric field between the two plates of the capacitor. I know that it's going to be from plus to minus from our Coulomb's law. Even from our Coulomb's law we can write this. So I draw this electric field. This is all nice, well and good. At this point P, from my understanding of my divergence, what should be the divergence at the point P? It has to be 0 because it's not really diverging out. What is the curl at P? Do you see that the vector is rotating around P? No, it is just parallel. So the curl is also 0. Why am I giving this example? Giving this example because now if you look at these points at the edges, the field lines are going to do this. Let me draw the bottom edge. So this is plus Q, this is minus Q. Field lines are going to be doing this from this edge to this edge. Now if I look at a point P here, neither is my divergence going to be 0 nor is my curl going to be 0. Because I still see some kind of rotation of the vector around this. The vector is changing its direction and it's also pointing in. So this is a case where I have non-zero divergence, non-zero curl at this point in vector space, right? So what does curl tell you? It tells you the effect of circulation. A curl gets represented as del cross A. Now how do you formally define it? In the vector space, if I want to calculate the curl at this point P, just like in divergence you estimated a unit volume around this, here you will consider a unit surface ds and find the circulation with the contour integral of the vector around this point. You find out what is a contour integral. What is contour integral? You have to do a line integral here, line integral here, you have to do a line integral here, line integral here of this vector. You do not know what the direction of that vector is. Vector could be this way. So to find the line integral, you have to take the projection of this vector along this direction, take the projection of this vector along this direction, projection of this vector along this direction, projection of this along the fourth direction. So use your fundamental understanding of line integrals, contour integral, calculate the complete contour integral of A dot dl, right, for this entire surface and then calculate that per unit surface area. Do the contour integral per unit surface area. Now put the limit that delta S tends to 0. That gives you the magnitude of curl. Story is not over, because if I have a vector field or a point here, let's say this is my surface, so my vector field is here, the surface is the surface of my paper. Around the same point, I could have chosen this as my surface or this as my surface or this as my surface. There is nothing that told me that I have to choose this as the surface. I could choose the surface in any direction around this field. So which surface should I choose? The answer is I should choose that surface for which this number is maximum. So I have a point in space around this point, this paper is representing the surface that I can choose around this point. So where am I calculating my contour integral? The vector could be pointing in, up or down or at random direction. Where am I calculating my contour integral? Across the 4 boundaries of this surface. 4 boundaries because I have chosen a nice rectangular surface. I choose a circular surface also, does not matter. So long as I am able to find the contour integral, it is fine. But which surface should I choose? The surface need not be horizontal or vertical or anything. The surface should be such that that contour integral is maximum. Which means when does a contour integral become maximum? When the vector is, when that cos theta component is 0. I am trying to align my surface along the direction of the field, right, as much as possible. So the maximum value, and you know that the maximum will happen only for a particular surface, right? My surface, it's not necessary that if I do a contour integral along this surface, when I change the surface, the contour integral could change. Why would the contour integral change? Because my angle is changing. The surface normal is changing. So I should have a direction also. So it is the maximum value in the direction AN. And what is that direction? So if, for example, in this case, this particular surface gave me the maximum value of the contour integral, the normal to this surface is the direction of curl. The normal to this surface which maximized the contour integral is the direction of curl. Alright. So what is AN? AN is the direction of the normal to the area which gave or which gives maximum circulation. So in a way what you are saying is, let us say for example, this is the surface which gives me maximum circulation. When could that have happened? When do you get maximum circulation? When I do a line integral over this, it should give me maximum. When would the line integral give me maximum? When the vector is lying along this line, the line integral is maximum. Along this. When would the line integral along this direction be maximum? When the vector is lying along this direction. Because your cos theta is 0. Cos theta is 1, theta is 0. When would the line integral along this edge be maximum? When the vector is along this. And when would the line integral across this be maximum? When the vector is across this. Which means you see that the vector is turning, it is along this direction and along this direction. Which means the vector has kind of rotated. That is where the circulation is maximum. And how do you fix a direction for this maximum circulation? You want to fix this, say that around this area the circulation is maximum, around this direction. How do you give a direction to this area? Direction to this area is given by the direction of the surface normal, right? So if I get, so this is your del cross A. If I say that the curl of A is, my answer is going to be a vector, is this, it simply means that the direction of the vector, let us say this is the direction of curl of A, not the magnitude, the direction of curl of A. What can I understand? I can understand that in an area normal to this direction of curl of A, I have the maximum circulation for this vector. If the direction of curl of A is, for example, pointing in this direction, it simply means that if I imagine a surface perpendicular to that, it is around that surface that the vector is curling. It is not around this it is curling. It is around this surface that the vector is curling. That is the meaning of curl. Alright. So how do I calculate this? It is simply cross product here, and you do the usual methods of cross product. So Ax, Ay, Az, because your del operator is having x component del over del x, del by del y, del by del z. A is Ax, Ay, Az, the x component of A, y component and z component. Do this determinant, I get curl of A. Right. So what we discussed today is the physical meaning of gradient, divergence, physical meaning of curl. Now one more thing before we close is, I can do an inverse operation here as well. If I do an inverse operation, this is a differential operation. What would be the inverse operation? It will be the integral of curl of A over a surface is nothing but contour integral A dot dl. If I do an inverse operation here, this is your Stokes theorem, which simply says that if I take the surface, around each point in the surface I keep taking the contour integral. I keep taking the contour integral. I take for each. I keep taking the curl. Curl is the circulation. I keep taking the circulation. The sum of all that nothing but the line integral, because the inside edges the circulation will get cancelled. The outside edges will be simply a contour integral A dot. So this theorem is also going to be useful later in electromagnetics. So we stop here today. What we will do in the next class on Thursday is do the Maxwell's equations. Alright, with this understanding of gradient, divergence and curl. So I open the class for questions. If you have any questions, please ask. So I have a question from CCAN. Very fine idea about divergence. If there is no source or sink inside the volume, the divergence will be 0, is it? Yes. Now it also depends on what you call as a source and the sink. If you mean that the source and the sink is the source of electric field and the sink of electric field, yes. Or it need not be electric field also, it could be any vector field. It could be source of water, for example. Think about divergence as, you know, what if you can think about water flow, velocity of water as a vector field, you get water is flowing out, there is also divergence. So the answer is yes. Very fine idea of curl, thanks. Okay, thank you very much. What else? If you have any questions, please hand raise or come on chat. Any questions? DC, are you? If there are any questions, please send an email to the QEEE team also, or ask me tomorrow when on Thursday when we meet again. Close the class now. Thank you.